in biology, we study plants and animals, and say we're thinking of a species, and when a biologist says, well, I know this animal, this means that when asked, we can answer questions like, okay, where do they live? How long do they live? Are they up during the daylight or during night? What do they eat? When they have how many offsprings do they have? And all kinds of questions. So I'm pretty sure that a list could be compiled of questions that if a biologist can answer all of those questions, they can state that yes, they do know this animal. Calculus is a little bit like that, only it's with functions. So imagine that there are a list of questions, important questions that we ask about a function, and if we can answer all those questions, we could say that we indeed know this function. We're going to call this complete analysis of a function. And we're going to start with a few questions to ask and study the functions from that point of view. Just two things about this list. Number one, it's going to grow over time as we're going to acquire new concepts. And Calculus 1, to a great extent, is developing techniques to answer exactly these questions. The other thing is that about this list of questions, oftentimes it's not just the answers that are interesting, but also the interaction between items on this list, between two questions, how they influence each other. We're going to see examples for that soon. Throughout this whole complete analysis of a function, there is going to be a recurring theme, and that is the connections between algebraic and visual things. And there is a back and forth between the two, so every algebraic property has a geometric manifestation and vice versa. And it will often be helpful to play one against each other. So sometimes we run into difficulties in one and then we switch to the other. So sometimes the visual is easier, sometimes the algebraic is easier. But there is this very strong connection that starts with the number line. If you think about the expression number line, so that connects things algebraic and geometric. This theme comes up very, very much in calculus. Okay, so the first question is often the easiest question, that is the question of domain. As you may know, a function is an assignment between elements of two sets, a non-empty set called the domain and another set called the range. And so what is the domain of a function? That is the first question on this list. The domain has to be either stated, so when we specify the function, we have to specify both the assignment and the domain. Because two functions, if they have the same assignment, they are not equal to each other unless they also have the same domain. So when we give a function, when we specify it, we must give both the assignment and the domain. We mathematicians like to cut down on writing, so we have this default or natural domain, which is the largest number set possible. For example, if our assignment is f of x equals 1 over x minus 2 and the domain is not given, then we use the natural domain, which is the set of all real numbers that can be meaningfully put into this expression. What does it mean meaningfully? That means that out comes a number and not undefined. And so when you're looking for domains, you're just going to have to ask what could go wrong here. How can I get undefined out of this? Because those things have to be ruled out. So the list of how can we get undefined is a short list. 3 ways we can get undefined: division by 0, negative number under a square root or fourth root or sixth root or other even root, or not strictly positive number in a logarithm. So this is the checklist, and this one obviously doesn't have any square roots, any roots or logarithms, so the only danger we should worry about is a possibility of division by 0, which actually is possible when x happens to be 2, right? We basically solve an equation for when is the denominator 0. So x is, so on paper this is a fine answer for the domain, but technically this is not a set. So we can say the domain is x such that x is not 2. Right now, I hope it's a fad, but right now interval notation is the buzz, and unfortunately I couldn't program my OpenMath to accept both inequality and interval notation. So I went with interval notation, even though personally I actually prefer the inequality notation. To write this in interval notation is basically from negative infinity till 2, then skip 2, and 2 to forever again. So that's how we write this set. This is regular set notation, this is interval notation, and this is the graph. Okay, so the domain of this function is the set of all real numbers except for 2. Okay, so the domain is either stated or we have to find it. And as I said, it is often the easiest question. Often the hardest question, and often the last one we answer, is range. The definition of a function is that it's an assignment, it's a unique assignment from a non-empty set called the domain, and the set of all x values, into another set called the range, which is a set of all y values. So while domain is the set of all x values, the range would be the set of all y values. And you will see that it will take a whole lot of work to come up with the range. It's going to be one of the last things we're going to do. After domain and range, the next item on our list of questions are the intercepts. So visually, when we graph a function, the intercepts are the points where the graph intersects the axis. Well, the things that I marked with orange are called the x-intercepts. And the thing that I marked with green is a y-intercept. Now notice that a function can have only one y-intercept because x equals 0 can have only one value assigned to it, but it can have plenty of x-intercepts. Okay, so we get the y-intercept if we just ask ourselves, what is the y value when x is 0? What is f of 0? The x-intercepts, we're going to have to ask, okay, now x has to be what so that f of x is 0? And one more comment, in this course, to avoid confusion, intercepts are points. If this point here is 0, 3, some books will say that the y-intercept is 3. We're not going to do that. We're going to say that the y-intercept is the point 0, 3. Every time we're talking about intercepts, that's a point, which means you're going to have to enter an ordered pair of numbers as answer. So why are the intercepts important? The y-intercept is important to us because that's when we substitute x, or very often t for time, equals to 0. In other words, the y-intercept reflects the initial conditions. That's when we start. So that's kind of significant. So it is reasonable that we are interested in y-intercepts. Now the x-intercepts, on the other hand, are also very important because, well, for one reason, they are solutions of equations. Suppose you have a 5-degree equation. How do we solve that? We reduce one side to 0, we factor the other side, and apply the zero product rule, right? So we're solving for zeros. Every time we solve a higher degree equation than degree 1, we are reducing one side to 0, and therefore we're looking for the 0 or x-intercept of an expression. So they're very naturally just solutions of equations, which is, again, a good reason to be interested in them. Okay, so what do we have? We have domain, range, and intercepts. So the x-intercepts often much more difficult. Okay, so next comes something very, very reasonable to ask, and that is maximums or minimums. You will see that half of this course is obsessed with finding maximums and minimums. And that is a very reasonable question to ask. So let's talk about visually. Here is an example. Now, visually, the maximum is the highest point on the graph. And so in this particular case, this would be what we call a maximum. The minimum would be, surprise, surprise, the lowest point on the graph. It's almost self-evident that we're very interested in maximums, minimums. We're often modeling all kinds of things with functions. Profits, for example. We would like to find maximums of profit functions and produce there. We want to minimize risk, minimize cost. So there are all kinds of things that we're modeling with functions. We're naturally interested in maximums, minimums. So visually, maximums, minimums are the highest or lowest point on the graph. What would that mean algebraically? So we just have to basically translate the idea of the concept of highest point and lowest point to algebra. That's all. So suppose f is a function. Again, in our class, maximums, minimums too will be points. So that means you have to enter an order of pairs as opposed to just a number. So it's not just a maximum value, it's x coordinate, y coordinate. Okay. Suppose that f is a function. The point, so this is a point on the graph, right? This is the x coordinate and this is the y coordinate, and m is for maximum. I usually capitalize for maximum, lowercase for minimum. Is a maximum if, so the point xm, f of xm is a maximum if for all x in the domain f of x, so these are all the other x values, right? For this to be a maximum, back to the picture, for this point to be a maximum, that means that this has the highest y value, right? So except for one thing, that it doesn't have to be the single highest point on the graph, just as long as no one is above it. In other words, you can have more than one maximum point. Just think about, for example, the sine function, y equals sine of x. Because our definition allowed equality, that means that wherever sine takes 1, those are all maximums. So you can have more than one maximum point, as long as the other point's y coordinate is equal or less. So nobody is higher. So that's the definition, that's the algebraic description of a maximum. Minimum goes similarly, you just reverse this inequality sign, right? So a point xm, f of xm is a minimum if for all x in the domain, f of x would be greater than or equal to f of x of m. Now, in order to come up with the range, for example, we would have to find the maximums and minimums. Even though they come in order as domain range, intercepts, and maximum minimum, usually you need to know what these two are so that you can find the range. Okay, the next item on this list of questions, is whether this function is one-to-one or not. That's a yes or no question. So, as it turns out, one-to-one or not is a very important property of functions. We will see examples why. So, just a side note, there is another word for one-to-one, a fancy, snobbish word. It's injective, and I kind of like that word, injective. So, what is one-to-oneness? So a function is one-to-one if no 2x gets the same y. So it's not just a matter of one value, but between two elements of the domain, they should each have different. So let me give you an example. Suppose the domain is the set of all people taking this class. And the function would be the final grade that you're going to get after this class. Now, a one-to-one function would mean that no two students have the same grade. So this has to be a pretty small class, right? Just one person can get an A, one a B, and so on. So that's a one-to-one function. If you have a function where you just find two x values with the same y value, that's it, the function is no longer one-to-one. And there are two ways to say one-to-one, and they are both kind of important. So let's state both. So a function is one-to-one if for all a and b numbers in the domain, if a and b are different, then the function values assigned to them must be different as well. Now there's another way to say that, which is logically equivalent. I don't want to rewrite these two lines. So a function f is one-to-one if for all a, b in the domain, if f of a equals to f of b, then a equals to b. So that says that if you're landing on the same number, f of a equals to f of b, the only way under a one-to-one function that is possible, that you started at the same place, that a equals to b. So they both pop up often. So when we talk about one-to-one, we return to this bubble representation of functions. Domain range, Okay, so these are three examples that you might see. The first bubble represents the domain, the second one represents the range, and so we depicted the assignments. So this one is not even a function. Not a function. Why not? Because this element of the domain is misbehaving. You see, there is a branching here that is not allowed. You cannot have two different y values assigned to the same x value. So because of this situation here, this is not a function. Now this one here is a function because there is just one line coming out from every element of the domains. However, this branching here is depicting a function that is not one-to-one. You have two different elements of the domain landing in the same element of the range. This is a function, but not one-to-one. And now this is what a one-to-one function looks like. This is why I like the name injective, because later on you will see in mathematics that if you have a big set and you have a smaller set, and you define a function from the smaller set into a subset of the big set, and that function is one-to-one, then you're kind of injecting this system into the bigger one. You're just importing that structure, so to speak. Okay. How can we tell from a graph that a function is one-to-one? Well, sometimes it's good to be negative. We're going to be negative here. So how could a function fail to be one-to-one? That means a function is not one-to-one if you have two different x values with the same y value. Boom, this function is no longer one-to-one. We can test for that with something we call the horizontal line test. If we start with a horizontal line like this, and we scan through the y-axis, in case of a one-to-one function, these lines, these horizontal lines, would intersect the graph of the function at one point or no point. And so this here is a horizontal line that intersects the graph at actually 3 points, not just 2. And if you can just find one such a line, the function is no longer one-to-one. Okay. So finally, why is one-to-oneness so important? So we're going to see several reasons. So here is a question. If we know that a squared equals b squared, does that imply that a equals to b? And the same question, but instead of squaring, now multiply it by 5 and add 1. So we grab two numbers. We multiplied both of them by 5, added 1, and landed on the same number. Did we necessarily start with the same number? And the answer here, no. Opposites square to the same thing. We could have, right, if a equals to negative b, then this is true. So just because two numbers square to the same thing, that doesn't imply that they're equal. On the other hand, this is going to be true. So if 5a plus 1 equals to 5b plus 1, then a equals to b. Now, what makes the difference? Here, in case of squaring, we use the function f of x equals x squared. And here, to both sides, we applied 5x plus 1. This function, squaring, is not one-to-one, which means you can start with two different numbers and land on the same y value. Which is why this conclusion cannot work. You do not have to be equal so that your squares are equal. You could be opposites. On the other hand, this conclusion is correct because this is a one-to-one function. You can easily see that it passes the horizontal line test. So whether a function is one-to-one or not, that has a great deal to do with what steps are allowed in equations. When we solve equations and when we make a step that preserves the solution set is called an equivalent step. And so steps are always equivalent. If you're applying one-to-one functions to both sides, we can go back and forth. That is not the case with not one-to-one functions. We're going to see later on in the course, we're going to see other reasons why one-to-one functions are so useful. Okay. And the final item on this list is the graph. Now, the graph is not a separate item or property, but rather the summary of everything. So if you can graph a function, you really know it well, basically, because a graph pretty much contains all this information. Without knowing these things, we cannot draw a precise, realistic graph. Okay, so let's see a few examples now. Okay, now let's see an example. We're going to give the complete analysis of 3 similar functions first. Our first one is f of x equals 1/3 x plus 2. Since the domain is not given, we have to find the natural domain, which is the set of all real numbers that can be meaningfully substituted into this expression, which means we don't get undefined. Well, to get undefined, we would need division by 0, negative number under an even root, or negative or 0 in a logarithm. None of these are possible here. So that means that the domain is the set of all real numbers. Unfortunately, on my open math, you're going to have to enter an interval. So if we graph this function, we know what straight lines look like, right? Now, given the form of the equation, this is the slope-intercept form, we can very easily find the y-intercept. Well, the y-intercept is always easy, right? Just substitute x equals 0. So if x is 0, y is 2, so 0, 2 is the y-intercept. For the x-intercept, we're going to have to ask, for the y-intercept, we said x is 0, y is what? Now we have to go the other way around for the y-intercept. X is what, so y is 0. So we have to solve the equation 1/3 x plus 2 equals to 0. Subtract 2, multiply by 3, I'm getting negative 6. So we subtract 2, multiply by 3, so we get x equals negative 6, which makes sense because we know what a straight line with slope 1/3 looks like. 3 to the right, 1 up, 3 to the right, 1 up, 3 to the right, 1 up, right? That's the dancing pattern. A negative 6, 0 x-intercept makes sense. It kind of works with the rest of the problem. So we see this, the shape of the line, and the fact that the domain is perfect, the set of all real numbers, this shows that there is not going to be a lowest y value, and there's not going to be a highest value. So for maximum, minimum, please don't write infinity. Infinity is not a number. That is one reason already why I don't like interval notation, because it suggests that infinity is a number, which it is not. The maximum has to be a fixed point, one number. For any point on the graph, there is a higher one. Therefore, maximum, there is none, and there is no minimum either. So the domain turned out to be all real numbers. The y-intercept was 0, 2. The x-intercept was negative 6, 0. There was no maximum and minimum. And now we can go back to the range and realize that every single y value will be taken eventually. So the range is the same as the domain, the set of all real numbers. And finally, is it 1-to-1? And if we apply the horizontal line test, we see that it passes it, so it is 1-to-1. And well, we kind of had the graph already before. Okay, so now let's look at one that is similar, yet it's going to turn out to be very different. Okay, so this function has the same assignment but a different domain, and keep an eye on how just a little bit of a change in the domain will affect all the other items in this list of questions. So let's see. The domain was given, right? So the domain is negative 6 to 6, closed interval. Closed interval means the endpoints are included. In inequality notation, x is locked in between negative 6 and 6, and so it's less than or equal. We're going to wait with the range, right? Because for that, we need to know everything. It's good to know that given the assignment, we're talking about a part of this infinite straight line. And so let's keep going. So we already computed the x and the y-intercepts, right? The x-intercept was negative 6, 0, and the y-intercept 0, 2. We just substitute x equals 0, right? Let's just figure out what this function does at x equals 6. So 6 over 3 is 2, 2 plus 2 is 4, so we have 6, 4. So actually our graph looks like this. So it is just a closed interval of a slice from this infinite straight line. And watch how a lot of things will be affected. Now the whole the straight line over the set of real numbers had no maximums, minimums. Now we have both, right? The maximum, the highest point on the graph, is 6, 4. The maximum value is 4 when x is 6. And there is a minimum as well, which is negative 6, 0. So it coincides with the x-intercept, right? Okay, now we can go back to the range. Because in this particular case, the range is really all the numbers between the minimum and maximum, right? So the range is, we're going from 0 to 4, right? And it's a closed interval because 0 and 4 are taken as y values. So this would be the inequality notation. This is the interval notation. It's still one-to-one, and we already graphed it. Next, what we're going to look at is the same thing, but instead of the closed interval, we're going to use negative 6 to 6, the open interval. So there's going to be a lot of similarities. For example, this is a slice from the same graph. Actually, there's not that much difference. It's just the endpoints are represented by empty bubbles, which means that the endpoint is not included. But still, this was negative 6, 0, 0, 2, 6, 4. So let's see. Domain was given. The range, now that we have this graph, because we have looked at this line several times already, we can just see that it's going to go from 0 to 4, but it's going to be an open interval, right? No number in this interval will have a 0 assigned to it, because the one that does is negative 6 is not in the set. Maximum, minimum. That's a huge difference between open and closed intervals. In an open interval, so as it turns out, this set does not have a smallest element. Negative 6 is a good candidate, but that's not in the set. But then, among the numbers that are, there's not the smallest one. What, negative 5.9? Well, how about negative 5.99? How about negative 5.99999? The problem, and now again we run to the geometry to argue the following. If you have a number that is greater than negative 6, then basically you can zoom into this picture and find plenty more numbers between negative 6 and then that number. And then grab this smallest one and zoom in again. And if we zoom in enough, the picture is the same as was before. And we can continue this forever. So basically, there is not a smallest, it's sort of open-ended. I like the expression open because it's kind of, you can march towards the smallest number forever and never reach it. So there is no maximum, no minimum. Oh, I forgot the intercept. So the intercepts. If you have a one-to-one function and all we do is just take out numbers from its domain, then it will have to remain one-to-one. So yes, this function is one-to-one. And we already have the graph. Okay, so we're going to look at a very similar example where we're going to take the same assignment on 3 different domains. So the assignment is a quadratic expression. So before we even do anything, we're going to factor this by completing the square, because when we do that, we can find all kinds of information, not just the intercepts, but more importantly, the vertex. We're going to factor out negative 2. So the multiplication backwards should work. And now inside the parentheses, we're going to complete the square. Half of negative 6 is negative 3. So our complete square, the one towards which we're going to push our expression to, is x minus 3 squared, which when expanded is x squared minus 6x plus 9. So we're going to smuggle in that 9. Okay, so this expression is called completing the square. This is a complete square. And now that we have that plus 9 after the x squared minus 6x, it is a complete square. So these 3 terms can be rewritten as the complete square x minus 3 squared. And then we just combine these 2 numbers. This is called a standard form. That is the form that will tell us where the vertex is. And now here we're going to just factor via the difference of squares theorem. 4 is 2 squared, so we have x minus 3 plus 2, x minus 3 minus 2. And then we just clean up. So we have negative 2 times. And then we clean up. So we have negative 2 times x minus 1 times x minus 5. Now let's see. We learn a whole lot of things from this. Now let's start with the vertex, because that's the most interesting one here. The vertex has to do with the idea that squares have a possible lowest value that is 0. Well, it is possible to get 0 as a square, just square 0. On the other hand, we cannot get below 0 because that would be negative, and real numbers, none of them squares to a negative number. Quadratic expressions, unlike linear ones, have a very natural minimum, which can turn into a maximum, like in this case. So, a square, let it be x squared or x minus 3 squared, is 0 or positive, right? If you look at this expression, x minus 3 squared, is it possible to get a 0 out of this? And the answer is yes. If x is 3, 3 minus 3 is 0, 0 squared is 0. And we cannot get below 0. So this one has a lowest possible value, and it's 0 when x is 3. I like this form because this tells you the following. This here is a positive number, or maybe 0, but it's 0 or positive. We multiply it by 2, it's still 0 and positive. And then we subtract that from 8. So from 8 we can subtract 0, that would be 8. From 8 we can subtract 1, we get 7. Or 10, we get negative 2. So this thing will have, this is going to be an upside down parabola, and this is going to have a maximum. Right, because 8 is going to be the maximum value we can get out of this, because this expression is 8 minus 2 times a positive or 0. So it's either less than 8 or maybe equal to 8. So the vertex is going to be when x is 3, and then it's going to be 8. Also, from the negative leading coefficient, we know that this is an upside down parabola, and therefore we kind of expect it to have a maximum. The last line will tell you where the x-intercepts are, right? Because this is what we do to solve for the zeros. This product is 0 when x is 1 or when x is 5. So these are the x-intercepts. Now the y-intercept, just substitute 0 anywhere. But actually the easiest is in a polynomial, because in case of a polynomial, everything that has x is 0. So it's just negative 10. So we know the y-intercept is negative 10. So I'm starting with the vertex, which is 3, 8. And then it comes down from both directions. And then when x is 1 and when x is 5, those are x-intercepts. And then the y-intercept is 0, negative 10. See, just these points from all these computations kind of gave away the whole game. Right, here is the graph. Domain. So what is the domain here? We don't have any division by unknown. We don't have any division, let alone a division. This is the expression. Every real number can do this. We can square every real number and then multiply by negative 2 and so on. There is no division, there is no even root, and there is no logarithm. So we cannot get undefined out of this. So the domain is perfect, the set of all real numbers. Now that we know what the graph is, but notice that we also know what the maximum is, right? So let's skip range again, and let's go for maximum minimum. And this too is very typical to a quadratic expression. If you think about x squared, it has a lowest value, but not the highest. Now this one was flipped upside down. This one was flipped upside down, so this one has a highest value, but not lowest. So there is a maximum, and the maximum is the 0.38, the vertex of the parabola, and the minimum, it doesn't exist. And so the range is from negative infinity. What is the highest y value that is taken? 8. So it's this part is closed. We can never get to infinity. So that part cannot be bracket. Okay, what else do we need? Domain range. Oh, the intercepts. Basically, we found those. So the x-intercept is 1, 0, and 5, 0. The y-intercept is 0, negative 10. And the last question, since we already have the graph, is this function 1 to 1? And the answer is no, very badly not 1 to 1. Even the 2 x-intercepts means game over, right? We have 1 and 5, two different values for x that have the same value for y, namely 0. So this one fails the horizontal line test just about everywhere. This is the exception. So this is badly not 1 to 1. Not 1 to 1. So now what we're going to do is we're going to look at the same assignment, so this parabola basically, but by restricting the domain, we're going to take out different chunks. So let's first look at the same assignment, but the function will be different because we're restricting the domain to... When you have the same formula and you just computed something, recomputing it again is not something mathematicians do. There's no pride in it. So let's just use what we have so far. So we mathematicians don't like to perform the same two computation twice. So let's just use what we have. We know what this parabola looks like, right? So it has a vertex at 3, 8. It has x-intercepts at 1 and 5. And y-intercept in 0, negative 10. So this is a parabola. This is the parabola from which we're going to take out a slice. Let's find f of 2. F of 2 would be, we just substitute 2 into the function. I'm getting negative 4. Let us also compute f of 6. And we get negative 10, which kind of makes sense. There is this outer symmetry. Okay. So what this means is that our function was restricted to the domain from 2 to 6. And that means that we're capturing this part of the graph. Okay, and now we're ready to answer. All those questions. So let's start with the domain. So the domain was given to be the closed interval from 2 to 6. The range, well, now that we have the picture, it's quite easy. It's the closed interval. The lowest y value is negative 10. The highest one is 8. So it's from negative 10 till 8. The intercepts, I keep forgetting the intercept. So the x-intercept, we lost one. This one is no longer in the domain. Even though the computation will spit it out as a 0, it's not in the domain. So we're just left with this one, which is 5, 0. And the y-intercept, we lost that one too, right? This one, this graph, does not intersect the y-axis, so there is no y-intercept. So we have domain range, maximum, minimum. So the maximum is the vertex, so that's the point 3, 8. And while the parabola on the entire real number line did not have a minimum, this one does. Because of the restriction, the minimum is this point, 6, negative 10. And finally, is this parabola 1 to 1? And the answer is no. This part here fails the horizontal line test. Not this part, but this part does. And just one bad line is enough. So this is not 1 to 1. And we have the graph. Okay. So the next thing we're going to do is we're going to look at the same assignment, but the domain is going to be given as the open interval between 2 and 6. See how different things will become. So I'm just going to copy the picture. So the question is the same, only the domain is given as an open interval. So now the assignment is still the same, but the domain is an open interval. And you will see it causes huge differences. So the intercepts. The x-intercept is still 5, 0. We lost the other one just like before. The y-intercept we lost. The domain was given. The domain was given, not the range. This is an interesting situation because we're used to sort of closed interval gives us closed intervals and open interval gives us open intervals. The y values range from negative 10 to 8. But 8 is taken and negative 10 isn't. So this is a half open, half closed interval. So that's sort of interesting. Maximum, the maximum is 3, 8, the vertex. And the minimum, there is no minimum. And finally, this is still not a one-to-one function. Thank you for watching.